organized places. Actually, I have to say that I started a bit working on the resurgence because I learned that you will organize this program here. And I was convinced my colleague János Palog, you can see as an author there, who was an expert in solving WIGNER hop techniques, integral lactation, and it was obvious there is a resurgence behind, so he wanted to understand resurgence. And I heard many talks from Ines before, and I thought this is a good arena where we could work out some details. So I will talk about resurgence into the OM sigma models, and then we have a series of papers on archive in collaboration with these guys, Michael Eotvos, who was our postdoc. He's a postdoc now at Yale. János Palog, I told you he's an expert in these integrable models and WIGNER hop techniques. Árpád Hegedűs, who is a younger research fellow, quite experienced in numerically solving thermodynamic Bajnok lactation. Saida Sadayan was an Iranian postdoc, and then she got a permanent position in Iran now, and our very talented PhD student István Volán. So I would like to state first the problem, and then I would actually use the terminology challenge. That this is not a problem, it's really a challenge we would like to solve. So what is the challenge? The challenge is that we have this unknown function, this chi, which satisfies some linear integral equation with the kernel k, and some right-hand side is cosh alpha theta. Alpha is the parameter, and this function lives in the interval, actually between -b and b. We would like to solve this linear integral equation, and then we would like to calculate some observable, which is like this cosine hyperbolic beta times the solution. And we would like to analyze the expansion of this observable in a small parameter. I learned this is small parameter is important in research in the school a year before. So the small parameter is 1/beta, and then we will see that there is a trans-series solution, and it goes into the exponent e to the beta, and sometimes we also have log b term, but we can resum usually the log b into the 1/b by introducing some running up. So we would like to get a complete trans-series solution for these linear integral equations and observables. And I just point out that not all these observables are independent, because you can derive very easily in a two-line calculation some relation between this the derivative of this observable can be expressed actually the boundary value of this unknown function and the product of the boundary value. So this is the scheme and the framework in which we would like to work today. We're not differential equation integral. What is K? K is the kernel, I will show. It depends on the model. So this framework is quite general, and depending what is K, I will describe different situations. So let me just list a few interesting cases depending what K is. So this is the kind of motivation. You remember I have this linear integral equation and the observable. And then one primary example is two-dimensional integrable quantum field theories coupled to a conserved charge. In this case, this K kernel is the logarithmic derivative of the scattering matrix. And the observable is the energy density and the density. And for example, there are many integrable models, and then the one I'm going to describe in more detail today is the OM sigma model. And the OM sigma model, so the S matrix takes this form, which is the product of gamma functions, and then this ratio, the parameter n appears in the argument of the gamma function, and it's related to the delta in this way. So 1/delta is n minus 2. And there are very similar models with different S matrices, like the n again, n equals 1 supersymmetric extension of this one model, and there is the Grossner version with another different S matrix, the principal chiral field, out of which the simplest, the SU2, is just the over sigma model. So like this S matrix with n equals 4. And then if you specify a bit more this parameter n, like 3, then you will find that the kernel is particularly simple. This is just a rational function. So this is also a very interesting case. And this is related to the WIGNER model and also the Godon model in the statistical physics. Even more, it's also related to a classical electrodynamical problem. Just imagine two coaxial disks, and you put some charge on it and maybe opposite charge, and then you would like to calculate the potential. And then in order to calculate this potential, you have to solve actually a linear integral equation. Exactly the integral equation I'm going to talk about. And in this,
sorry, what is A in that case?
This one.
The same current.
It's the same. Yeah, it's the same. Yeah. And depending what is Q, if they are charged the same, then the kernel has a different sign. If they charge oppositely, then this is the kernel. So this is the Maxwell-Kirchhoff electrodynamical problem. And then you would like to calculate the capacity, actually, as a function of this dimensionless ratio, which is the ratio between the radius of the disk and the distance. And then you can make some perturbation theory when this A is large or this B is large, because then this is like a high school problem. But it's notoriously difficult actually to expand this problem, even perturbation. But I will explain. So this is the plan of the talk, and I have to apologize because it's going to be a technical talk, and I know I have a mixed audience. So I would like to give all of you something new. That's the idea. So don't be scared if you feel this is completely out of your scope and you don't understand. I will come back. So I will have several parts. The first part, for example, is just the introduction of the model. This is mostly for physicists. So I will actually derive this linear integral equation, how it comes out from physics. And I also would like to emphasize in this part that there is some path integral behind. So what we learned here, it might be valid also for higher dimensional counterparts like QC. Because these models, the O1 models, are very similar to QCD in two respects. They are asymptotically free and they have a dynamically generated matrix. The second part, I will do an asymptotic analysis, really how to see the resurgence. And this is a kind of maybe experimental mathematics, because I will be able to calculate 2000 terms very high precision, and I could see the asymptotic behavior, and I will try to extract the analytic structure on the Borel polynomial. This is the second part, and we will see some interesting relations, and then later I will show how you could actually derive those relations, some of those relations. Then I will make the similar analysis in the O3 model and or this capacitor problem, and then you will see this is quite different. So while in the O4 model, we will see that the perturbative coefficients carry all the information about the non-perturbative structure. This is no longer true for the O3 model. And then I will show how actually you can use and expand this integral equation using the Wiener-Hopf technique or improved Wiener-Hopf technique. And you can get this is again a general N calculation, and this is basically the general solution of the problem, how you could extract the trans series from the linear integral equation. It's valid for any N. It's not really related to the rest of the talk. And I will conclude and provide some. So there's the plan. So let's see how I define this model. So this is a quantum field theory in 1 + 1 dimension for n scalar fields, which satisfy this constraint. So this is the nonlinear sigma model. So the scalar fields live on the sphere, and you have a Lagrangian. And what you do, because it has ON symmetry, you pick up one of the ON generators, and then you couple a magnetic field to this conserved charge, and then this is the Lagrangian you would like to analyze. There is the bear coupling, which is going to be pressed up to the running coupling. Actually, this Lagrangian has a special form. You see, this is the Euclidean Lagrangian. We have this I, and you see I have this H squared term. It is Hamiltonian, just this form, that the original Hamiltonian minus h, the magnetic field, times the charge. So then this is the Lagrangian. And what I can do perturbation theory. So because I have only n-1 independent fields, I expand one of these guys, the phi 1, say, in terms of the other, and I do a path integral for the remaining variable. And what I calculate the free energy density. And from the free energy density, I can introduce by Lorand transformation the density and the ground state energy. And these are the observables I would like to describe. So although there is this path integral, and there are quantum field theoretic techniques how you can evaluate this path integral perturbatively, but this is quite difficult. And then so far we could calculate from the Lagrangian only the first 3 terms. But it's not very hard to go higher order. So what helps is that this is an integrable theory. So you can derive for the same observable a linear integral equation. How can you derive this integral equation? So while the Lagrangian relies on the ultraviolet description of the theory, the integrability starts from the infrared. So in the infrared, you have particles, in this model n particles, and they are integrable, so when they scatter, they don't create more particles, just stays the same. And what is nice about this magnetic field we introduced, that 2 particles will be charged, for example, one of the ON charges in this model out of the n particles. One will be a bit heavier, and the other is a bit lighter. So the energy will be modified, like the dispersion relation plus minus magnetic field. And by varying the magnetic field, I can actually decrease over n, and then the negatively charged particles will condense into the particle. And then I can exactly describe the energy and the density of this state, how I do it. So I just put in a finite volume n particles there, and then I see how moments are quantized. So if I bring one guy around the circle, then the momentum will be quantized, not because of the translational phase, but also because I scatter on all other particles. So this is how the F matrix appears. So the ground state is determined basically the scattering, and then you can derive in the thermodynamic limit this from the beta ansatz. So this is basically the thermodynamic limit of this beta ansatz equation on the right. So from this, you can derive this linear integral equation, and the kernel what appears is the logarithmic derivative of the scattering. So this is how it comes out. And then you can calculate the density and the ground state energy just by integrating this rapidity density, what we solve by solving this linear integral equation. Comparing to the previous problem, we should invert this relation between the density and V, and then express the ground state energy in terms of the density, and this is the natural variable, what we would get from after the Lorand transform the Lagrangian picture. So you would think that having this integral equation is easy to make a perturbative expansion, but this is not true. Actually, to calculate the first 2 terms, it took some time, and this was a famous paper by Hazen, Franz Majore, and Niedermeyer, because this is how they could relate the ultraviolet parameters to the infrared parameters. A new insight came from Dimavoli, who actually, it has some origin also what is called actually matched asymptotics. And his idea was to introduce, instead of this unknown function chi, the resolvent. The resolvent is a function which has a cut on the theta plane, such that if you calculate the jump of this function, this is the chi itself. So using the resolvent and using the Laplace transform of the resolvent, then he could parameterize in the same time both the resolvent and this Laplace transform. So, for example, in this theta space, So we have two descriptions. One is the resolvent itself as a function of theta. I'm just explaining this idea. The other is the Laplace transform of the resolvent as the function of n. The Laplace transforms operate in the function near the endpoint at B. And from the WIGNER solution, you can parameterize the solution by its asymptotics, which can be exactly determined, and also some unknown function is Q. And in the same time, how it behaves around the origin, knowing that you have this jump, you can also parameterize the function here in terms of this. And matching the two asymptotics, miraculously, all these coefficients can be uniquely determined, the CNM and the Q. So that was his idea. And once you determine it, then you can expand the rho, the density, in terms of 1 over B necessary. There is some prefactor which is like A to the B, you see here. And also you can express this energy density in a power state. So this is how we can calculate the perturbative coefficient, a very large number of perturbative coefficients. And this method can be extended for other problems of the same form for other kernels. So let's see what is the structure. So this rho hat and epsilon hat, when I remove every proportionality, the series starts with 1, and they are an expansion in 1 over b, the small parameters. And then doing his method, this Wolins method, I can calculate all these coefficients. So what is the structure of this coefficient? So I just put the first few terms here, and you see there is this quantity, this a ln2. How I abbreviate it, so it appears this ln2 in the expansion, and also theta function. These are what. So the nth order, you got an expression whose transcendentality is exactly n. So that a theta n has a transcendentality n, and this log 2 has transcendentality 1. And then typically you have the most general term what you can imagine, and then fixing this coefficient, you get some numbers. But doing this calculation, you can imagine analytically. But already at 22, Dima Wolin could go to 22 order, maybe in like a few hours running of his computer. But the expression gets bulkier because you have more and more data expression. So there is this other nice paper by Marcos Marino and Tomasz Ray, and then they could go to 44 coefficients. And then we could go to 50. But it's nice to have 50 coefficients, but if you would like to do an asymptotic analysis, it's still not enough. And then if you would like to make correspondence to the field theoretic description, then in the field theory, you have the running coupling, and you would like to express everything in terms of the running coupling. So then I just put this expression here, because you can transform all this expansion rho of B, epsilon of B, as the free energy density as a function of the running coupling.
That's alpha. Alpha is the running.
Alpha is the running coupling. Yeah, I can go in more details if you want. I have some formulas how it's defined, but basically it's defined from B and rho. I guess I have some questions. Yeah, so this is the definition of alpha. So once you calculate rho and B, you can define this alpha running coupling. And what is nice about this alpha, this is exactly what you would do if you do a Lagrangian perturbation. So we can compare to the previously calculated string coefficients, and they are the same. And then you would believe if you could really expand the Lagrangian, you got the same.
But at the beginning, I thought alpha and B were independent parameters, but now they're linked by this.
No, they are linked, absolutely. So you have like 3 parameters, if you want. You could have age, but they are basically the same, just they are related to each other. The magnetic field, you have this B, and then you have alpha. But you can express or rho. You could also take rho. Rho and the age, the magnetic field, are dual with respect to this Lorand transform. Okay. Sure.
For these and also how do you do with that one?
You exponentiate this expression. Yes, and then you plug back to this perturbative expansion, and you match the curve.
When I'm doing exponentiation, then you have these times out.
Yeah. So alpha is small in the perturbative expansion, B is large. So that's the 1 over.
You have to make an
1 over B is alpha. Yeah, it's like that.
So you have to make the assumptions about how large small d times out to invert things, or is it really
No, it's maybe it's a bit formal series actually. These series are asymptotical. So it's very formal. I just make an expansion like alpha as a function, expansion in 1 over B, and I using this relation, for example, I show the first.
What I meant is like imagine that you have terms that would show up as d times alpha, exponential times alpha. That one would that be large or that be small. So I'm just asking if when you're doing the inversion, whether you ever encounter something like that.
No. It's easy. Okay, so these are the coefficients, and then analytically we can get the first least square. So now I'm explaining a kind of experimental mathematics. So if we would like to see asymptotics and resurgence, we don't really need the analysis for. So the idea was, so why don't we do it numerically? And that's what I will do. Just before I would like to make this point. So this original first few terms from the integral equation was calculated by Hazen, Major, and Wiedemeyer, and it's a very famous calculation because now you have two calculations. One from the Lagrangian, having the Lagrangian parameter, which is the running coupling, or the running coupling can be parameterized also by the mass gap, say, in the MS bar scheme, the dynamically generated. On the other hand, in the expansion of the TPA, you use the mass of the particles. By matching these two expansions, actually they could match the lambda MS bar to the mass of the particles. And this was the first calculation of this type, and then it's really unique. And this is the ratio, I just put it here. So this is the relation between this lambda MS bar and the mass of the particles. And later it was extended for many more. Okay, but I wanted to do numerical. So what we did is we used actually not that big computer powers. The O4 model is sort in this respect is much simpler than the others because you don't have log B terms. So here we could go really very far. We could calculate in the expansion of this row, for example, the first 2,000 coefficients with 7,000 digits using mathematics. And then we did the same for the energy. And then when you extract the free energy, you lose some digits, but still it's a lot, 1,400. And then what you will see is that they grow exponentially. They go like factorial. So how can you see it? So you can just divide, take this form with Cn, that combination of the perturbative coefficients, for example. It doesn't matter, you could do it with U, psi, or you could do it with this guy. So here what I'm showing, I'm showing how it approaches actually a constant. Yeah.
What is the role of big N? Because in your Lagrangian, it looks like only the first two are coupled.
No. So big N is how many fields you have.
Yeah.
Of course, if you have a lot of fields, it helps. Here I'm talking about only O4, but everything depends on N. So, but in the Lagrangian also, let me show you that. So when you express here, for example, phi1 squared.
So what I was asking about is you have phi1 and phi.
And then you have what others.
Yeah, but that can just be written as phi1 squared minus phi2 squared.
Yeah.
out of the entry?
No. Here, the kinetic term, you also have all the other signs. And then, for example, not all of them are independent. So you express phi 1 as a square root of this right-hand side. And you plug back the square root, for example, here, and then you will have all of it. I'm very nasty only now.
So sort of a larger limit.
No. The larger limit is simpler. I would like really work for fixed small f. I'm talking now about asymptotics. Yes, but the calculation based on the Lagrangian kind of stops at this level. So we replace the calculation based on the Lagrangian by the integral equation, which we calculated facultatively. This is where we are now. So we can calculate this path integral, we expand it around the trivial saddle, and then somehow we are so clever because it's an integrable theory, we can calculate 2000 terms. This is really exceptional. In quantum field theory, we cannot calculate 2000 terms, but in this quantum field theory, we can. So we have these 2000 terms in the O4 model, and then now we are just playing this game. Let's understand what physics is inside. So let's see what is the physics. So first of all, if we form this combination, then we see that it has a constant as asymptotic. So this is asymptotic. It has some constant and then -1 to the n alternating another constant, and then there are 1 over n corrections. And then for example, to extract this constant, how constant it is, then you can do this resurgent transform. So you can speed up the convergence. So you can actually project on either the positive or the symmetric or anti-symmetric part. And say if you project on the symmetric, then you have an expansion that is a constant, something 1 over n, something 1 over n square, and so on. And then just making certain clever combinations of these perturbative coefficients, you can suppress actually the correction. And then you can very clearly see what is this point. And then what I'm showing here, I subtracted this constant asymptotics, and I would like to see how quickly it goes. And then because I have 2000 coefficients, it's extremely quick. You see that sometimes this is, if you just keep like 100 terms, this is as close as 10 to the -1. So it's you can really extract all these coefficients. But what can you do with these coefficients, which are factorially growing? And then what you would do, and you all know, just in this talk I was a bit more general, you could go to the Borel plane. But if you actually have a path integral formulation, this Borel function is very natural, because you are calculating, say, the path integral, and then let's assume I just fix the value of the action, and I perform the path integral for that fixed value, and then integrate for the length. So this is nothing but immediately the Borel transform. So the physics is really the Borel transform. Okay. So what is the Borel plane? So I have a lot of coefficients. No? I go to the Borel plane. So I already defined these coefficients, but I would like to define a function as on the Borel plane, see, with this coefficient. And then I would like to see the analysis. And the first thing I could do is the body approximant. And then I will see a cut on the negative line, negative field line, starting at -1. I can see a pole at 1, and I can see a cut starting at 2. This is what immediately you get.
How do you tell whether it's a or cut?
No, it's everything pole. I mean, here it's because it's a body approximant, everything is just pole. But when you see that they are very, very dense and condensing, yeah, I will show. Yeah, they are actually logarithmic. Yeah, and then it follows from there. So we can go to the Borel plane. So question here: how we give meaning of this this asymptotic series, and then how we would like to calculate maybe to the path integral or something else. Or actually, we would like to compare to the numerical solution of the integral equation. So what we do in order, we have this last integral, and but you see, because we have singularities on the real line, we have to sort of decide that which way we go a bit away of the singularities. Of course, we could. This is the lateral or a resummation. We could go a bit up or a bit below of the singularity, and depending whether we go up or below, we got different results, and we have an ambiguity, actually, an exponentially small ambiguity in the way we go. For example, if we have a pole, then the residue of the pole will give an ambiguity, non-perturbative ambiguity into this form. And then, of course, you have this other guy, so you will have other ambiguity. So we did this numerical evaluation of this integral, and then in the study approximant is not that good, so we use the conformal mapping. Maybe actually I will explain the next slide. And then we improved it considerably. So we could calculate very precisely, numerically, this lateral Borel resummation. So this is actually the detail. So you can use this conformal mapping, and then you can transform the original perturbative expansion in this variable, and then you can perform very precisely this integral. So you will have the numerical value, which give the meaning of this asymptotic. And then, so we did this calculation from the perturbative series, and we wanted to compare to the numerical solution of the TP. So what we did is solve numerically, or practically actually we used some Chebyshev basis, and then we calculated the energy and the energy density, or density and energy density for 30 digits. And then we could compare what we got here. The first observation, when you do this calculation here, this lateral Borel summation, then your result will have an imaginary part. So, but just taking a look of the imaginary part from the numbers, you can fit this theory. But you can this number here. But what is also maybe even more surprising, that you compare the real part, and the real part will also have a deviation. What you calculated here, it will deviate from the TPA numeric with a very, very small exponential terms, but nevertheless, we were so precise we could fit this D100. Okay, question. Can we understand these numbers, C's and D's, from the asymptotics of the perturbative series, because it should contain all information? And the answer is yes. And then let's see how it comes out. And this is the answer of your question. How do I know they are cast? What sort of cast? So you can see very precisely that this perturbative coefficient will have two parts, and then the odd part and the even part. And then they have this expansion of this form. Like you have the constant asymptotics, and you have 1 over n times n minus n corrections, and even you see that the next correction comes like 2 to the minus n times a similar form. So in the Borel plane, this actually means that this is a cut. Why? Because if you just take, for example, this term and you plug back to this form and you sum up, you see that is going to be, this will give rise to a pole at -1. If you plug back this one, the next term, 1 over n term, then you will see that this is a logarithmic cup multiplied with the feeder. Okay, so fitting all these terms to basically fit the perturbative expansion of the function which multiplies this slope. Okay, this function in this terminology is denoted by the alien derivative of this original function at that singular position. Okay, so what you can see from the asymptotics that we have a cut here. So there is some alien derivative. There is a function starting from here. There is a pole here at 1, and then you will see that there is a cut starting there. Okay, so how precisely you can see? So because we had the like 2,000 coefficients, 7,000 digits. So So you got a number, for example, in fitting the asymptotics, there's lots of digits. And then you can look up. There are web pages like this, but you can do it actually recently also already in Mathematica. You can fit this expression, yeah, and then you can see that this is E over 8 pi, or I don't know, 150 digits. And then, so you can fit, because the structure is quite similar we had before, then you just make an answer, and then this program actually will tell you what are those numbers. So we could fit all this number, the first 20, or maybe not so much, maybe 7 analytically, and then numerically we know like another 8 here. So we could calculate the alien derivative of this function what we analyzed, the perturbative expansion of this term, which characterizes the first cut, not so precisely as the original, but still very precisely. And then we could see that the singularity on the Borel plane at 1 is indeed the pole, because this other guy was 0 for hundreds of digits. And then we could also calculate that alien derivative. This is the singularity as 2. Again, very precise. So the analytic structure looks something like this. We have a pole, we have this cut here, and then we have this other cut. This is the nearest interval. And again, now, because we know this is the structure, we could perform this lateral Borel resummation, and we could see that the imaginary part actually should be these coefficients, which are now fitted analytically many digits. But and then you could compare what you got when you compare to the TBA. But this was, and then they are the same coefficients. But what about the real ambiguity? How can we extract the real ambiguity? And the idea is that you have to go further. You have to analyze the cut actually, which started as 2, and the function which multiplied the cut there, because that function, it's also, that expansion is asymptotic. So that function will also have a cut. And then, but this is the cut of the cut of the cut, and then there is a calculus that very nicely resums all these things. And this is actually the Stokes automorphism, which take care what happens with your function. This is a Stokes line. So there is an ambiguity if you integrate a bit above and below, and then you should just see what happens if you change the integration and how you should change your function such that the integral would be the same. This is called the Stokes automorphism. And then the Stokes automorphism exponentiate all these cuts. I mean the alien derivative of I define. So if you know the alien derivative of the alien derivative, then you know the Stokes automorphism and you know how to your function jump. And the median resummation is that you have to take the square root of this Stokes automorphism in order to define the physical value. This is like not integrating above that below, but just on the halfway. So you will integrate a bit above, but the function you integrate is just the square root of the Stokes. And this should be the physical answer. And then if you do the calculation, you will see that what appears here, for example, in the physical value what should come out, what you should integrate, it has these terms as higher alien derivative. So for example, it has the second alien derivative of the original function twice. That's the jump of the jump. So in order to, we would like to see this real deviation, we need the jump of the jump. Yeah. And then we had 80 terms. So we could, for the jump, so we could calculate, I think that we could see the jump, and we could see that indeed these terms were the same, but we measured from the numerical deviation. So that's one part. And then we also found something interesting and unexpected. And this was the behavior around the cut at -1. And then we do not have an explanation why this happened, but this is an observation. So we start, and then here we analyze the resurgent structures, not in the running coupling, but in B. So we analyze how this rho, for example, what is the analytical structure of the density as a function of E. And we could see, for example, we have a cut at -1, and then we calculate the jump function. And then we realize that this jump function is actually the same function researched there, to a certain sense, so maybe resurgent. That the jump and this cut, it was just a product of epsilon and rho. And then if you could calculate the jump of epsilon, and it was epsilon squared. Like delta -1 is just multiplying with epsilon. So it's very surprising. And then you could calculate also the alien derivatives at one of them was 0, the other was constant. But the alien derivative at this cut, it's a sub-u function, couldn't relate to all. And then so we started to analyze the analytic structure of the functions multiplying at the cut, and then we could see they also have a cut at -1 and another cut at 2, and then this was some new function. But here again, the resurgence at -1, it could be expressed in terms of all functions. So this is what came. And then even you could define some nice combinations, like epsilon divided by rho and 1 over rho. And they were nice in the sense that this delta 1 and delta -1 alien derivatives moved in a very simple way. So it was like a two-component system. You could move from one to the other, but you couldn't move further, or you could, with delta -1, you could move back, and then you could also, you cannot move further. So still no understanding yet, but this is very nice. Actually, if you act with delta 2, you will get two guys which behave the same. So it's sort of expected that it should be like two dimensions, and one dimension behaves so simply, the other dimensions behave more complicated. All these new functions. And now we could do this maybe on resummation, because we calculated this delta 2. And then if it did it, then we exactly got back the previously measured deviation from the CBA and the Borel resummation. And then we checked numerically that it's very perfect. So this is about this experimental numerics about the O4. But for example, we got this very nice relation, and then we were interested, could we derive this relation or these numbers, what I showed you analytically? And then the coming slide is, yeah, not yet. So yeah, maybe I explained it. So what we could see from here, that there is some transferring, but we just analyzed the asymptotics, so we couldn't really see the whole transferring. We could see very small part of it. So we expect, for example, that this quantity, what we could calculate from the TBA, it has a transferring of this form. When the first piece is the perturbative coefficient, and from the asymptotics of the perturbative coefficient, we could see the contribution of the pole as the leading asymptotic, the leading piece here. And then we could see some subleading terms still from the Lorand asymptotics of the perturbative guys. And from the Lorand asymptotics of this first transferring term, we could see the next term, but we couldn't see it. So this is so far we could go. And this is what I wanted to show. Something that what I wanted to just show on one slide, how we could actually just confirm everything analytically I said so far in the O4 model. You remember we matched these two expansion. I told you that was Wolin's idea, that you parameterize the resolvent in this way, the Laplace transform that way, and there was some relation between the T and Q coefficients. And then what appears here is basically the expansion of this function, what appears here, the Taylor expansion expansion of this function. These are the A coefficients. And then if you expand, also Taylor expand this square root functions, then you have this E coefficient. And then, so these are basically the relation. And then what we did analytically, we could invert this relation and formulate closed system of affiliation only for the Q. And then, so that's what we did. So the Q's live on this outer plane, and then you could express in terms of each other in a recursive way. So you just move into this way and calculate all these coefficients. So since you have this closed recursion relation for the Q's, you could analyze how they behave analytically. So especially if n is large, we could analytically solve in this domain, and then we could make an ansatz in this other domain, which we fixed just by the recursion. So we could calculate completely the singularity structure, the alien derivative around -1 and 1. And then we got exactly the same for this more general observable, what we have seen before. So everything I told you, which was experimental mathematics, which was in this setting confirmed. And then what we did, that was O4. So let's try O3. Okay, so we did exactly the same I told you in O3. Although this is a bit more complicated problem, we couldn't calculate 2000 coefficients. We could calculate 336 coefficients. And then, so we first, we could see that indeed it's growing like factorial. If you divide by n-1 factorial, it has a constant asymptotics. You go to the Borel plane, you see the analytic structure. The first thing you will see that you don't have any cut at -1. No singularity actually on the negative real line, only on the positive. You have one pole, you have the cut. So you would do the same. You start to fit this coefficient numerically with very high precision. You got this term, you fit them, and then you see how this coefficient behaves. This is the cut of the cut in the previous logic. And then you see they still go factorial. You could fit the first two coefficients. And then you solve numerically the equation. You calculate the Borel transform, and you compare. Imaginary part is completely reproduced by this asymptotical behavior. And you expect that the real deviation should be like e to the -8 over alpha. This is the cut of the cut. And then what you really find is this is no longer true. Actually, there is a much stronger behavior e to the 2 minus alpha, and the whole series there. So this part, this is like in a next term in the trans series, is not reproduced at all by the asymptotics of the passive one. So this is a really completely different situation. And the O3 model is the only one which has an instant on. So most probably this is the contribution of the instant on. And those others are related to the normal, which actually was confirmed in the last sentence by Marcos Marino and his collaborators. So this is what we observed, and the question is that can we derive this whole thing from the integral equation, this trans series structure? And the answer is yes. And this is the last part I would like to explain now. And I will be here a bit sketchy. So I just show the steps how you can solve such an integral equation. And the first problem with the integral equation is that this unknown function lives only on the interval between -b and b. If it would live on the whole line, this integral is easy, it's just Fourier transform. But it lives only on the interval. So the idea is to extend the integral equation for the whole line on the price that there are some unknown functions which live only outside and which compensate the integral equation for that one. So these are more unknown, but then at least it's defined on the whole line. So first step, extend the integral equation for the whole line. And then now you could use Fourier transform. So now you Fourier transform your equation, and then you have still there is the Fourier transform. and then you just invert this 1 minus k kernel. So invert the kernel, and the idea, this linear hop idea, is that because your functions actually live only on the part of the real line, so the Fourier transform has a specific analytic structure. So it is, if you shift properly, I mean, if they live on the negative or positive half line, then the Fourier transform would be analytic on the upper and the lower half plane. So by appropriately shifting this function, then you solve basically the equation I will show you in a minute in such a way that you separate for the analytic on the upper and lower half plane part. So the first, what you have to do when you invert the kernel, you have to write the kernel in the two pieces. One is analytic in the lower, the other is analytic on the upper half plane. And then when you divide, you just multiply like G minus and G plus will leave it there. And so this is the same equation which with the redefinition of the kernels and the function. But this plus minus actually shows which is analytic on the lower and the upper half. So your integral equation after Fourier solution takes this form. And then you just project this equation analytic on the lower and the upper half. So for example, if you project analytic on the lower half plane, you see the function we need actually is not there, but the unknown function will appear in this equation. And then the chi, what we will need. So once we solve this equation for analytic on the lower half plane part, this unknown x function, we could calculate from here, and then plug back here and we calculate the function what we need. And then the observable can be obtained from this function evaluating that. So that's the idea. And then if your function is bounded and goes to 0 at omega going to infinity, then you can use this operator which projects actually to the upper and lower analytic part. So the integral equation which comes out after a bit more redefinition of the unknown function has this form. This alpha was the ratio of the decomposition of the two kernels, and Q is the unknown function. And then originally this integral went on the real line. And then knowing the analytic structure of the kernel, of course, this starts to depend on the model you are analyzing. And in this class of models, the kernel has the cup on the imaginary line, imaginary positive line, and it has also poles there. So you can deform the integral on the real line just around the imaginary, positive imaginary x, and so around the singularities. And what happens that you can investigate the residues of the pole. And then what you will find that there is an exceptional pole in the O3 model, whose residue you could pick up. And then otherwise, all the poles have a compensating residue. So if you just replace this integral with the principal value integral, then it's a completely well-defined and good equation. For just one unknown function defined on the imaginary, positive imaginary line. So this is the equation you should solve, but this doesn't have the trans-series structure. And the nice idea which came from the work of Marino, Mirazia, right, was that instead of doing such a principal value integration, let's shift the cup away from the pole and then shift your contour just around the cut. So you integrate the jump and additionally you integrate the pole. And if you do so, then you can rewrite your integral equation into this form. And this already has this trans-series structure because you will see these Q guys, which are the residues of the unknown function at the pole position. They always come into e to the -4, some expression, model dependent expression times b. So this is already in this trans-series form, and that you can solve order by order. Actually, we observed that you can introduce a running coupling in this sense and replace B with the running coupling, such that in other models, not like not only O4, this log B dependence completely disappears. And then you have only power series in this V coupling. And we did the calculation. Actually, also in this paper, that was a calculation for in the O4, O3 model, using the integral equation, you can calculate this exponential, the leading exponentially real correction, this coefficient exact. And then you calculate it, you compare the numerics, and they are the same. So this integral equation provides you this expansion, which is probably the instanton action and the fluctuations of all these instantons. So if you could do the calculation, it would be very nice to represent. So this is the generic solution, and in particular, what comes out for the O3. And then we did many calculations for other O's and higher terms based on this integral equation. Okay, so let me conclude. So using that, we had this also the integrable description of the problem, we could calculate many terms in which just did O3 and O4 numerically high order terms in this model, and then we could reveal the analytic structure of the functions on the Borel plane. And then using these analytic structures, we could see this exponential correction, the imaginary part and also the real part. And then we could compare to the TBA solution, and then we found complete agreement. And then, although in the O4, it was a complete agreement in the sense that from the asymptotics of the perturbative series, you could recover all higher, we believe, all higher Tron series terms, but this is no longer true in the O3 because probably because in the O3 you also have the instanton. But definitely, if you check the asymptotics of the perturbative coefficients, it doesn't know about the nearest Tron series coefficients at all. Imagine it knows about the imaginary part, but not the real part. But the imaginary part is just a pole. Yes, but the integral equation has all the information. So you could expand this using this technique, the integral equation, and then you can calculate actually all higher Tron series terms and the perturbative expansion of all Tron series if you have enough time and energy and ambition. Yeah. So that's about the conclusions and some open problems. So there are many interesting problems, and I just leave it here. So you can read. So thank you very much.
Behavior are related. Those are the ones that we know are related to large order behavior.
Yeah.
So
I know.
why they? I would have thought that this object, but because of this object, is not.
Yeah. Interesting. Yeah, I know. That is the standard belief. But you see, for if n is not free, then you don't have instantons at all. You have renormal. And in the large n limit, actually you can see what are those diagrams. So instanton, usually if you have a perturbative series and you have this exponential factorial growth, if you have instantons, it's related to the fact that you have more and more Feynman diagrams. Yeah, but renormalon happens when you don't have more Feynman diagrams, but certain Feynman diagrams actually give a contribution which diverge factorially if you go. So here you can see for large n that they are indeed renormal. So for large n, not n3, for then everything there in the Tron series most probably is renormal. So, so what you could do instead of using these variables on the sphere, you could project stereographically on the plane, okay? And then you have this plane variable. And then you can also, because it's 2 dimensions, you can introduce complex coordinates on the plane. So those functions, projected functions, which depends only on the holomorphic part, like Z, those are the instantons. So like a 1 instanton, when this projected variable looks like Z minus Z1 divided by Z minus Z2. On the multi-instanton, when you take product of it. So they are basically holomorphic or anti-holomorphic functions, and then depending how many poles you have, then that many instances. I guess so. Yeah. I mean, they are BPS solutions. So the action is exactly the topological chart, and then that you can calculate from the map.
Yeah. Looks like you have
Yeah.
So if you were to do a conformal map, which you did, you could actually, there are ways of uncovering what's going on other schema sheets marked by space and zero one. And I wonder if you could use that, because essentially what it does is it actually gives you information on what's going on in other sheets of some kind of universal mapping, which uncovers information on other remasters. So, and that essentially is the numerical tool, but precise information is yours. And get all the information, depending on the number of facts.
Yeah.
And access a lot of information.
Yeah, it's very interesting. And I have to tell you that we were not able directly to get the information about higher tasks on the same Riemann surface, on the same sheet, say. Because somehow the leading cut was so strong. And then when we calculated the Edian derivative and this function multiplying the logarithmic cut, it was also asymptotic. So it influenced also the behavior around the next cut. Yeah, and I learned that you could do it actually by this uniformizing maps and that, but we haven't explored. But it's on the list we would like to do actually. Yeah. It's on. Okay, I will ask. Yeah. Thank you.
You had the numbers where these that were returning success on the alien derivation. Right. This looks a lot like this.
This one? Yeah.
Yeah, this is for the roles there.
Yeah.
Looks a lot like this. Most like this on the like basically when power tries to find the nice base for research function, like getting searches like easier to use.
Oh, I don't know anything about but I will take a look. Thank you.
Your Wiener method, would that work also in the Eotvos?
Sure. It's very general, yeah. And then when we developed it, we actually developed for generic N. So it also works for any N and O4 too. But there is this, so in the WIGNER language, you can explicitly see the difference between O3 and any higher N, ON. And the difference is this extra source term, which exists only for O3. So O4, we don't have this term, but still this is valid, this format expansion. Yeah.
So is this approach easier or harder than the approach calculated in 2000?
So actually we should combine the two, because in this approach, at some point you have to invert. For example, you would like to solve, say, this equation and then calculate the perturbative coefficients from this term. Then you forgot about all the exponential terms, and then you would like to solve this integral equation. And then you could expand this beta, because the coupling is somewhere here, so you expand beta, and this is this airy kernel. See, it's e to the minus, say, x, then the unknown function x plus y, and then the unknown function here, and that you would like to invert at first order. But you expand this beta and you expand the unknown function, so you have to apply this airy kernel many times, and then this is how you could calculate the perturbative coefficient. And then there was this, so before the work of Marino and his collaborators, they could manage to do it mostly numerically and conjecture the perturbative coefficients from this approach. And later it was slightly extended analytically, but even with the approach of Marino, they could go maybe third order. But it's very complicated to invert this kernel, and even to calculate the perturbative coefficient seems hopeless. However, from the other approach, you can go as many orders as you want because it's recursive. And then you could get analytically 50 terms. Here, inverting this integral equation is hopeless. But if you combine the two, then I believe that you could calculate all these coefficients at any order, basically at one. Okay. Thank you.